This right here is a fun little project that I've been working on, which is glowing beer. So this is meant to kind of produce glowing beer.
This is Elliot Roth, founder of Cellsius, a community biolab. We took a trip to San Francisco to check out Elliot's lab and to see firsthand how accessible bioengineering has become, what you can learn from taking classes at a community lab, and whether or not we should worry about small labs creating dangerous viruses or bioweapons.
So Cellsius as a community lab came together in order to lower the barrier to entry for people getting involved in working with DNA and becoming DNA literate. Just like people learning computer technology, right now it's going to be ever more important that people learn how to interact and work with biotechnology in order to start working with organisms in these self-replicating systems to make amazing things.
So you're teaching a course that is associated with MIT. Tell me about that course and what do people learn from it?
So we started teaching how to grow almost anything. It's a course through MIT, through their community biology program. What people end up doing is they take like a literal MIT course where they're learning everything from how to isolate DNA, how to analyze DNA, how to design and build their own DNA, how to reintroduce that back into organisms like bacteria in order to express and create all sorts of amazing things. And it introduces many topics that are at the very cutting edge, from using new AI models to design proteins to learning how to produce at large scale different kind of biological constructs. Currently, the barrier to entry for most people getting involved in biotechnology is one of three things. So either location, it's very difficult to actually understand what is required and what materials and equipment is required. The knowledge and know-how, which is available online, but it's hard to parse and put together from everyday papers. And so you might need some sort of guidance, mentorship, and expertise. And then the actual equipment itself that's required. And so most of the equipment that we have in the laboratory space has been donated or shared or gathered over years and years, and is meant to kind of provide access to people to be able to start working with DNA. Of the equipment here, the basics that you kind of need are a clean surface of some sort. This has recirculation in here. You need something to incubate right here. You need something to cool or keep everything cold. You need a pressure cooker. Maybe you need a centrifuge sometimes. You need that. Sometimes you need a microscope. There's something called a PCR machine. So this right here, these are two different versions of the same kind of thing, but you can have it as small as like a little USB stick. And this just heats and cools things really, really fast. So this is the machine that doubles DNA. This is the same thing. So you can go from very small amounts of DNA to like quite a bit of DNA very, very rapidly. And then the other thing that's somewhat necessary is we have a big power supply here. And then a microwave. I don't know. That's kind of it. I can plug this guy in. You can see how it works. Here we go. I can go here and I can say, all right, like let me set up PCR. And you can have a certain start temperature. Once that's all set up, I can say set, and I can run the PCR. Go like this, and it'll heat up this little thing right here. And it'll do that off of my laptop battery. This is the blue fluorescent protein that was growing over there. And so you have different parts and pieces of it from restriction enzymes and whatnot, but I can go into a sequence map.
If you're looking for a PCR machine or other basic lab equipment for a small biolab, the Odin is a great place to start. They sell DIY genetic engineering kits starting at $199. For the full home lab kit, it's about $1,600. Or if you had a PCR machine, it's about $2,500. So what exactly is synthetic biology, and how does that differ from non-synthetic biology?
Synthetic biology is the practice of engineering biology. And so what you're doing is you're taking designs that you either create or imagine and going about designing the DNA that then programs life and reprograms life in a particular type of way to go about creating something new. And you're doing that as a means of solving global challenges and problems, whether it relates to climate or it relates to human biology or anything in between. I think the realm of possibility is limited in essence by our imagination. And so many of the people who are coming into the class are limited in understanding what you are able to get access to. And I think given any sufficient span of time, you would be able to work on and kind of put together drugs in some kind of way, or different aspects of improving, enhancing, editing, changing, healing your own biological state. It depends on your motivation. It depends on, how much you want to focus on that task at hand. One of the key challenges that we face here in a shared laboratory space is that people come and go and walk in between whenever we're doing experiments all the time. So we're working towards more sterile space, cleaner space, so that you can start working with human cells. We have a group in our laboratory that's working with brain organoid systems. And so so brain organoids are tiny little brains that you're able to take from stem cells. And so you can make these little tiny brains, and some of the questions being asked are, what is the minimum viable consciousness? Like how do you actually interface with dead or damaged tissue that might be from like limbs missing or other things like that? And so those kind of questions haven't been able to be asked, particularly because the level of sterility and the amount of access to those kind of spaces has been really limited. And so being able to open up those tools, a possibility to other people, enable you to also get access to some of the questions that you're not really able to answer. So as an example of like a therapeutic of some sort, you'd want to test that with an animal population. Well, you can't do that right now in any kind of community lab space.
Where are we at with people in nefarious places maybe creating scary viruses or any other, doomsday scenarios? Should we be worried about this?
Well, so I get the question of, can somebody do a scary thing in the laboratory all the time? And in fact, we had somebody from Open Philanthropy show up to our class and ask whether or not we could use an LLM to create a virus. And he was like, hey man, can you teach me how to make a virus? And I was like, are you wearing a wire? Like, what are you doing? And I think the main barrier is really a number of different things, but in essence, the ordering of DNA is really tightly controlled to make sure that you're not ordering certain sequences. Like you could not recreate a virus based on the sequences that you ordered. Granted, those kind of systems can be gamed and can be hacked and worked around. But the caveat to that, and the main thing that I would caution and urge, is that one of the best ways to deal with challenges associated with people who are trying to do something malicious or nefarious is by having more people involved and more eyes on what's happening. And so rather than restricting and constraining a particular technology, it's just going to pop up somewhere else. It's better to enable other people who might be those white hat hackers, the people who are going to be doing beneficial things and things that go about helping and enabling people to counteract more nefarious people. Also, one of the key challenges in biology is that it's just hard to get anything to work in the first place. You're dealing with things on a microscopic scale, and you're far more likely to harm yourself if you're trying to do something that's pathogenic or dangerous than you are to hurt somebody else. And I'd be more concerned with countries actually doing these kind of things than I would be concerned with individuals.
If you personally had all the money and resources in the world at your disposal, what projects would you work on?
So if I had all the money in the world and all the time in the world, I'd be working on some of the projects I'm already working on part-time and just kind of in my free time. There's a number of projects that I think are really interesting and important when you take a look at the context of what is going on in the world. So one of those projects is a soil bacteria that can break down landmines. And so there was a enzymatic pathway that degrades RDX, which is one of the main components in landmines. And landmines still kill about 5,000 people every single year, mostly children. And they cover the surface of area that's about the size of Wyoming. And so it's kind of wild when you think that this is still a big issue in the world. And in fact, a third of Ukraine is now at risk of dangerous landmines covering its surface. And so to open up productive agricultural land, to prevent children from dying, all those kind of things, that's one of the projects that I aim to start chipping away at in the laboratory.
To learn more about the Cellsius Community Lab or to sign up for a class, check out Cellsius.org. Also see the links in the description of this video for more resources.